So now we're continuing on with class number 10 and bearings, and we're going to introduce this idea of reliability. Now this is more statistics. If you had me for ME470, we did a short section in statistics where we covered just this normal distribution, right? It was we did it in conjunction with safety factors, right, where we have a distribution that looks like a bell. Well, for some industries and some applications, they found just over time that there's that bell shape didn't really accurately or reliably repeatably, I should probably say that, reliability, gave you the distribution wasn't really a bell shape, that there was a skew to it. So instead of having this Gaussian distribution, which is the bell shape, we can introduce something that we call a Weibull distribution. So this is a Weibull right here. And we can establish this thing we call reliability is going to be equal to this exponent right here over our typical E, right? So it's going to be E to this thing raised up here, and these parameters are given by by manufacturer, right? The manufacturer over time they do the statistics and they plot up what the distribution of their failures are going to be, and they figure out that here is what it seems, the parameters of our skewed bell shape. So you can kind of see this plot right here shows you this exponent b that's inside this other exponent, right? We're taking exponent to the exponent. You can see that there's like an 8 that gets put over here, or as opposed to a 1.5 or a b that's like less than 1. You can kind of see that it has this slope thing right here, and it doesn't really do a very good job of having a peak. But now we have two different hypothetical manufacturers in this in Shigley. One is manufacturer 1 and they use the 90 million cycles as their rating. So all their catalogs say here, this is the load number that's associated with 90 million. And if you wanted something, and that's only 90% reliable, if you want something other than that, if you want a different reliability, usually more reliability, here are the parameters that you would use and you would plug in to try to find this right here, okay? So these parameters, we're going to use manufacturer 2 almost always. So you're going to see this x0 thingy as 0.02. This theta, I don't know why they pick theta. I think this is just like tradition. They using these. It doesn't have anything to do with angle. So we're just plugging these values in here, and then this b. This is probably the thing that's really most important when if you're trying to think through what this means. It's just describing the skew really of the bell, right? And remember that normal distribution, Gaussian, is a bell. This is a Weibull distribution, which kind of leans over to one side, right there. Something we should remember about reliability here is that reliability is a multiplier, right? So if you have one bearing that's 90% reliable and you have another bearing that's 90% reliable, the total reliability is going to be 81%, right? 0.9 times 0.9 is 0.81, pretty sure. And so remember that, right? So that we're going to, when I want a machine that has a total reliability of 81%, we would take the square root of it and make sure that we had a bearing that was 90% on each of the ends of the shaft right there. So we have a total machine reliability that would equal to 81%. But we might want larger than that, so we might take the square root of that reliability that's given. Also, I think we had these load factors that were right here, these application factors that we might want to have put in. I don't know why I didn't put that in earlier, but maybe I should have. Now, graphically, what's going to happen for us, as a practical matter, to be able to implement this reliability is that these are really going to be parallel lines that we're going to shift, right? So there was the first line was at a slope of 1 over a, but now on this log thing, if we want to increase reliability, we take a parallel line. So what that comes off as in all practicality right here for us is going to have this equation right here, right? And there's another equation for this, right? So we can there's actually two choices of equations I should point out, and one of them is for if the reliability is greater, the desired reliability. Remember, that's the D of the thing, and we're taking that ratio, that life ratio on the top here, and the thing on the bottom is the thing we're using to adjust for a different reliability. This equation is appropriate when the reliability is going to be greater than 90%. But if you wanted to downrate it right here, you can also use the other equation. So let me point that out right here. All right, so here is the equation that I've provided right there. That's for the 90%. You can see that this is an approximation right here. Now, I'm not quite sure why we didn't use this one all the time right here. So they're saying that this one, and you can see that it starts to break apart. They're pretty close to each other, but when you get below 90%, it doesn't do quite as well. It kind of goes off to the side. But these are like approximations, and I can't recall why it was that we would bother using this, but I tend to use this one. Maybe it's just that the logarithm, maybe not everybody had natural log on their calculator. Might have been back in the day. I don't know. Seems weird. It seems like if you're able to raise, your calculator can raise something to an exponent. It seems to me that you'd be able to have a natural log as part of your thing. So anyway, let's see. So that's what we're going to include in our examples right here. Did we have anything else in the slides that I wanted to show? Let me double check that. Boom. Okay, now we're just going to do an example now. So I'm going to take Shigley Problem 1111 out of the book here. And for the bearing application specifications of 650 pounds for 5 years, 40 hours per week, 400 revolutions per minute at 95% reliability, determine the basic load rating for a ball bearing with which to enter a bearing catalog for manufacturer 2 and table 11.6, right? So they're telling us the table 11.6 is the one that I showed you previously that has the Weibull factors that you use. Assume an application factor of 1. Right, and I also noted that they gave us the loading in pounds, so we're going to want to have turn this into newtons later on. Maybe we want to do it right away. Let me see what they did. So we have for the bearing application specifications given there. Okay, so I start off here, and from this table right in here, I know that my rated life is going to be 1e6 revolutions. I got my XO is going to be 0.02. My theta is 4.459, and my B is 1.483. All right, so first off, I want to take my load. Let me turn that into newtons. So 4.448 newtons per pound is, so we have 2,891 newtons, which is 2.891 kilonewtons, right? And our desired, and then it's just for one bearing, right? If they asked for the machine, they might have specified 95% machine reliability. If that was true, we would say 0.95, so we need 97.47 for each bearing. But maybe they meant for the bearing, so we could say that that would say if each bearing had that, we'd have 90.25% total reliability of the machine, right? The XD we could do that. We could actually put this all into one equation, but let's do this in piecemeal. Here's the desired life was, we see 5 years, 40 hours per week right there, and there's going to be 40 RPM is going to be right there, and we also have our 60, and we're going to divide it by that rated life right here, right? So we take 5, and I decided to go years times 52 weeks per year times our 40 hours per week times our 400 RPM, and then our 60 minutes per hour right there. That's what all that got right to there, and that's divided by 1E6. We find that we get 249.6 is our ratio of amount of cycles we're going to need to a million, right? So this actually comes out to 250 million cycles we want this thing to live to. So here is our parameter here. We assume AF is equal to 1. That's a decent enough assumption. And then we say that, okay, so C10 that we would have for this thing, we take the application factor times the FD, all going to be XD over our XO plus our theta minus XO to the 1 minus RD, that raised to the 1B, and all of that over to the 1A right here, right? So plug in some numbers in. We say 1, we have our 2.891. We take our 249.6, and our XO is 0.02. We're going to take our 4.459, add it to our 0.02, and we're going to take 1 minus 0.95 and raise it to the 1 over 1.483. Okay, all over 1 over 3. And if we do that, we get 21.48 kilonewtons. And just so you know, okay, so some things that might make it interesting to us. Let's take this as an in-between number right here. This whole thing underneath, like on the denominator right here, is 0.6088. Right? So recognize what that's doing is it's really increasing the amount of time right here, which is going to increase what the catalog is going to be doing by this 1 over 3 right here. So let's take that 0.6088 and just take the inverse of it, right? And you find that it's 1.643. So you can almost think of this whole thing on the bottom as just a multiplier, 1 over a multiplier, that's going to make the time longer, right? It says, well, okay, well, we're going to make the time longer, but overall, what we could see is, let's take a look at what this whole thing is going to be. That whole thing that's inside there, when you take that right there, you'll see that it's a multiplier of 7.429. So all we've really done is we've multiplied the load by a factor of 7.43 and to say, okay, well, we're going to need a bearing that can handle a lot more load at 1,000,000 cycles so that we can have more confidence, more reliability in that bearing when it comes to being able to survive our load. Right, so we have a load, and but we have an amount of time that we want, so we need to adjust what that is so we can pick it out of the catalog and get something that's going to last longer and be more reliable. And so if we go and we do that, once again, so we need a 21.48. So we come into our thing, and I think they said to use a deep groove again. They didn't say. Well, okay, so we could actually say, let's see, I'm double checking. Yeah, I don't see that it says deep groove. So we could go down and we could see once again, well, that's 19.5 is not enough for us. 25.5 is. Once again, it ends up being a 35 millimeter deep groove. If we were to come over here instead, we could see that we might need we could use also a 35. So that's kind of boring right there, right? So both of them came out to be 35 millimeters. And so like if that was, so like it makes sure our shaft is at least has that amount of diameter for in way of there. So we might need to use design something with a bigger shaft because the bearings drove it, or we might need to pick another kind of bearing. And we note, of course, we need to use a different exponent. We have to be careful there, but just as a preliminary thing, we could jump in and start to see what the load rating is for right here. So yeah, we could use a smaller one. We could use a 30 millimeter here for this rating right here, or we could use something at 25 maybe for here. But of course, we need to recalculate just to change this exponent from 1/3 to 1/3.333. We could check it right there. It might be worth our time, just as a means of comparison for the reliability, to try out the other reliability equation right there. The other equation to adjust for reliability is, of course, I used this one down here. We might want to check out this one just to see what we would get, right? Now, I find that it's kind of like interesting that they have two different ones in here. I don't know why they would want to do that. Can be simplified slightly for calculator entry by noting this right here. So what would be the difference right in here? So I'm going to now enter in, let's see, let's try out this x0 plus theta minus x0 times our natural log. Okay, so I think that goes up into there. And this is 1/RD. See if I'm doing that correct. Right, and then we take this and take it to the 1/B. Right, so 0.02, and you don't need to see this thing sideways. 0.02 plus 4.459 plus 0.02. And now we're going to say natural log of 1/0.95 raised to the 1/1.483. So I take 0.95, take the inverse of it, take the natural log, and that's my blue button I reach there. And then I take 1.483, take the inverse of that. Now I'm going to raise that other one to that one. That's this button right here. Boom. And it's going to be multiplied by 4. Is that plus or is that minus? I think it's supposed to be minus. I think I wrote plus when it should have been minus. Yeah, I should have written it as a minus. My math is correct, but my math was correct up here. But let's see, 4.459 and 0.02. We subtract it, we multiply that, and then add 0.02. So what we're left with here for this whole thing is 0.6191, right? Well, that's the difference that's be here. So let's see if we take the 249.6 and now we raise it to the that to the 1/3 and raise it. Yeah, raise it. I get 7.388 compared to this. and then we multiply it by the 2.891, and we get 21.36, right? So there's not much of a difference there. So I almost think just use this one right here, because they're saying this one's not good if you have to go below 90% reliability. So there is a 20-minute video for this example.